Hello, I'm Dr. William Schlosser, Washington State University, School of the Environment. This is my classroom.
That about 20,000 years ago, great ice sheets covered much of this part of North America. This was the most recent glacial advance of our current ice age. But around 18,000 years ago, global temperatures began to rise, and the ice sheets, some of them several miles thick, began to melt.
It's starting, Adam, I think. Adam, it's starting.
Oh wait, Jim, this is the big piece is starting to calve.
Let me call you back.
Call him back.
Okay, bye.
Still going?
Yeah, in that V section right there. Holy shit, look at that big bird rolling. All four are running, right?
Yeah. Look at that. You see how, look at the whole thing.
We're just observers, these two little dots on the side of the mountain. And we watched and recorded the largest witness calving event ever caught on tape.
Keep in mind, this glacial cooling event we will call the Ice Age was forming over the northern extent of North America, and specifically along the extent of British Columbia and Alberta, passing into Washington, Idaho, and Montana, globally starting 2.6 million years ago. But it was only starting to break apart about 11,700 years before present. Those flood basalts we keep talking about busted through the lithosphere about 17 to 14 million years ago. This means those flood basalts preceded the most recent ice age by over 10 million years. Flood basalts came first, then the ice age froze its way onto these lands. Both events are heavy. Think about the weight of flood basalt flows piled 2 to 3 miles thick. Then add on the weight of the glaciers, frozen water held in place for over 2.5 million years. This puts a lot of weight on the lithosphere, and this compresses the Earth's surface. This is not a small incident, and we'll come back to that again soon. As glacial ice broke, water and ice were destined to overtop those flood basalt lands, located downstream of the melting glaciers, scraping off soils, plants, animals, and everything else accumulated on these surfaces. It happened as the flowing icebergs and glaciers scraped off surface lands. This slurry of organic and inorganic materials ultimately became recycled at new resting places, some as glacial erratics, and some as fresh soils on new surfaces. The Missoula floods from Montana and the Bonneville flood from Utah, what we call the Ice Age floods, are surveyed here at an introductory level. And finally, the interaction between bedrock and fluid dynamics of the floodwater are highlighted through discussion of Ice Age erosional and depositional landforms. Key locations in the Pacific Northwest are featured, including the Snake River Canyon, Grand Coulee, Dry Falls, the Drumheller Channels, Wallula Gap, and the Columbia River Gorge.
The Pacific Northwest is famous for many things, including huge floods of lava that buried almost 40% of Washington, and floods of Ice Age water that created more than 2,000 square miles of scablands. What are the odds that such rare events both happened here in this corner of North America? We're just south of Lewiston, Idaho, at the mouth of Hell's Canyon, the lowest point in the state. The basalt bedrock here, the floods of lava, came out of deep cracks that formed in response to a heat source that's now in the state of Wyoming. A flood of water from a giant lake in Utah came all the way through southern Idaho, through Hell's Canyon, dropped rocks here, and the water made it to the Pacific Ocean. A giant lake in Montana flowed to the Cascades, got backed up to here, each of these layers representing a separate flood. The Columbia River basalts, the Bonneville flood, and the Missoula floods. Let's dig in together and learn about huge floods in the Pacific Northwest.
Remember, this started 2.6 million years ago. The glacial ice was assembling and building mass throughout this period. The global hydrological system witnessed the accumulation of moisture transition from atmospheric humidity, lakes, and ocean water to be sequestered in glaciers, frozen and held. Glaciers are heavy, locking up the atmospheric moisture in ice, and when precipitation did fall from the sky, it was snow. This image shows the glaciers advancing like a Pixar movie, but it took over 1 million years for the advance to lock into place. Then glaciers got thicker, spread out, and started to flow as frozen rivers, moving in slow motion. That went on for over 2.5 million years. Eventually, starting to break apart about 11,700 years before present, these glaciers started cutting loose. First, it started as melting snow and ice. Some was at the margins of the glacier, but another source was the increase in precipitation. Ocean levels globally were low, about 300 feet lower than they are today. But it was beginning to warm. Water vapor evaporated to increase humidity, and clouds formed. It rained and snowed more. That precipitation accumulated where it normally would, to flow into river channels. Rivers came together into lakes and larger rivers. But along the Clark Fork River in northwestern Montana, the river met an impenetrable wall. The glacier lobe was still standing, blocking the river's flow. This was along a glacial lobe that was over 3,000 feet thick. That caused the backed-up river some serious problems. It formed Glacial Lake Missoula, stretching into a 300-kilometer, 190-mile-long lake with 3 lobes. Eventually, liquid water filled the Clark Fork River Valley with a lake reaching over 2,000 feet deep. Think about a glass filled with ice cubes. You pour it full of water and eventually that ice floats to the top. The same happened to the ice dam crossing the Clark Fork River. The lake of over 2,000 feet deep buoyed the glacier. Lift it and water starts to rush out. Some under it, some through it, some by pulverizing it and transporting big chunks into the flow. This opened the glacial floodwaters into Lake Pend Oreille. That lake bed was a fraction of the size of Glacial Lake Missoula. It overflowed that in an instant, and then rushed down the Columbia River. Instead of turning north at Newport, as it does today, it spread across the landscape to scour a new path heading westerly. Then, where the Grand Coulee Dam would be built, the water force hit against another glacial lobe. Reroute to the south to scour a new path. This made Great Falls, a monster coulee, massive waterfall, and source of more soils and boulders to be transported away. This series of floods out of Glacial Lake Missoula happened not once or twice, but more like dozens of times, maybe 100 times, each giving example to the end of the Ice Age as a series of warming and cooling cycles. This Ice Age was really a series of ice ages, stacked together through time. Each freezing and warming event welcomed another Glacial Lake Missoula, and its rush out of Montana. Each time, make it again. Each time, it warmed and it was recycled through a new spin cycle. This was not a few-year series. It took tens or hundreds of thousands of years to freeze and thaw, making those 100 massive flood events that hydro-washed the water's path to the ocean. We will stay with this theme through this series to discover how that all came to make the landscapes we see today. As we start to reason this series out, think about the valleys we know. Each has a distinctive shape telling us what made them. Most initiate as a river channel. It was formed by water running downhill. That is the normal course of events that we know as these V-shaped valleys. When the river flows fast, it cuts into the river bottom by eroding some of the loose materials like soils, transforming them into sediments and flowing them downstream. When it meets a lake, the water flow slows, and sediment is dropped. Glaciers are like rivers, flowing in slow motion. It is solid ice that, under heavy weight and pressure, can flow downhill in the valley that might have once been a river. When this happens, the shape of the glacier forces its way downstream, scouring out trees, shrubs, grasses, soils, and rocks to create the new shape of force. Glaciers make U-shaped valleys, like is seen while climbing Snoqualmie Pass from North Bend to Ellensburg. Look for the U-shaped valley and you will see them, rounded on the bottom and all the way up the walls of the valley. Sometimes you will see convergent channels of the glacial river flow downstream. This is the slow motion we observe. This glacier along Glen Highway, east of Sutton, Alaska, may have been in motion continuously since the beginning of the current ice age 2.6 million years ago. These are massive events, and the best way I choose to think about them is to consider that the ice is only water that has its temperature taken to levels below freezing. At this state of physical form, it still volunteers to the forces of gravity and flows downhill as a force able to rip out trees, or chisel batholiths of granite, or sculpt layers of flood basalts. When they are gone, the U shape is left to remind us where they once flowed as ice and emblems of force. The coulee is a shape we can only know when we see one. A massive flood coulee is seen on Highway 26, approaching Othello from the east. Steep valley walls with flat-bottom channels are seen. A little stream might be at the bottom, but that was not what cut that valley. These valleys were formed by massive flood events. It was the Missoula flood, crushing from Dry Falls and passing Palouse Falls on its way to the ocean. Coulees are seen around the world, but in eastern Washington, they are seen where large water accumulations built up lakes of water, so large that they could not be drained only along the rivers they originally were destined to flow through. Water routes into new channels, scours out the surface to etch new pathways. This is what happened when glacial Lake Missoula bombed out of the ice dam near today's state lines of Idaho and Montana along the Clark Fork River. The routes those waters took made new paths of released resistance. Erosion resulting from the Missoula floods has extensively exposed the flood basalt lava flows, laying bare many layers at Wallula Gap, the lower Palouse River, the Columbia River Gorge, and throughout the channeled scablands. When you look at these large and flat-bottom river valleys, seek a river and find there are none to be seen. The river flow that made these channels is long gone now. But sometimes there is a river, wide valley, flat bottom, and a little trickle of water at the bottom. The Palouse River is an imposter. This river at Palouse Falls meandered down the channel etched by the Missoula floods and meanders along fault lines in the flood basalt layers. The massive floods scoured out the landscape. When all was settled, this little river wanders down this path, jumping over the falls. This is the same river flowing past Nil Public Library and under Grand Avenue in Pullman. It could never have created this path or made that waterfall without some massive help.
This is Missoula and the campus of the University of Montana. A terrific setting in the Rocky Mountains, and ground zero for much of the water for the Ice Age floods of the Pacific Northwest. Let's tell the story in a nutshell and then explore old shorelines, high-energy gravel deposits, and delicate silt beds that all tell the incredible story of glacial Lake Missoula. During the Ice Age, the valleys of western Montana were filled with 1,000 feet of fresh water. Glacial Lake Missoula formed due to an ice dam in northern Idaho, the Purcell Trench lobe that blocked the Clark Fork River and its tributaries across the border in Montana. The ice dam area, which we know today as Lake Pend Oreille, was 2,000 feet high, 30 miles long, and sealed off a mountain valley, creating a backup of lake water 200 miles to the east. Like filling a bathtub with the drain plugged. A massive lake with long fjord-like arms. A southern arm that sat in the Bitterroot Valley to Hamilton, below Trapper Peak. An eastern arm to Drummond. A northern arm into the Mission Valley and the Mission Range. As the water deepened behind the dam, the pressure built against the ice sheet. Eventually, the ice was no match for the massive volume of water in the lake. The dam failed quickly. The lake drained quickly, just a few days, to drain and rush over the floors of the Clark Fork River and Flathead River Valley. The water barreled over eastern Washington, leaving deep cuts in the desert and moving tons of rock from the Rocky Mountains into Washington and Oregon. And that was one Missoula flood. But it happened again, at least twice, probably dozens of times, possibly as many as 100 times. The Purcell Ice Dam reformed, another glacial Lake Missoula, and a new Ice Age flood burst through Idaho when the lake reached a critical depth. Rinse and repeat. The floods took different routes based on their size and local conditions. In the channeled scablands of eastern Washington, thick deposits of loess, wind-blown silt, were swept away. A surprising amount of basalt bedrock was removed by the Missoula floods, leaving impressive box-shaped canyons like the Grand Coulee, with dry falls, fields of giant current ripples, huge potholes drilled into the bedrock. My God, how big were these floods? Regardless of size, each flood put on its brakes at Wallula Gap as the water funneled through the narrow gateway to the Columbia River Gorge. That was Lake Loess in southern Washington, a brief delay before the now dirty brown water continued on through the Columbia River Gorge and on to the Pacific Ocean. Okay, that's the story. It's almost impossible to believe, right?
Earlier, I mentioned Great Falls, south of Grand Coulee Dam. These falls were spectacular when water was falling here. Today, there is an unimpressive slack water pool behind the falls. Not even enough energy to fall over the cliff. Let's take a look at what made it so amazing.
Vic Baker from the University of Arizona has been studying this area for over 30 years.
Standing here in the middle of Scabland area, it's very difficult to get an impression of the scale. What you can't see from the ground is that this kind of topography extends over widths of 10, 20 miles.
In all, the Scablands comprise over 13,000 square miles, much of it remote.
As the glaciers were retreating, there was a tremendous amount of water that was released. And the result was that you had these giant lakes surrounding the ice.
One of these lakes we know as Lake Missoula. It formed behind an ice dam, created when a lobe of the retreating glacier blocked the Clark Fork River in what is now Idaho.
That lake held about 500 cubic miles of water and had a depth of 2,000 feet at the ice dam. So the pressure of all of that water, much more than behind any man-made dam, meant that the situation was set up for immense catastrophic floods.
One day, with a sound that can only be imagined, the ice dam let go, and the Lake Missoula megaflood surged toward Washington state, 150 miles away.
The hill I'm standing on is about 150 feet high, so the floodwater was at this point about 150 feet deep, and over behind me toward the Palouse River deeper than that.
100 miles later, the wall of water rushed past this point at around 50 miles an hour.
It would have in it blocks of ice, there would be boulders, animals, trees, absolutely frightening sight of immense proportions.
Today, we look over these lands with benefits of aerial photography, drone flights, and knowledge of what has transpired here. Consider the force of those massive flood waters, happening dozens of times, maybe 100 times, to rip loose the organic matter from these lands to create a flood surrey of water and destruction. Today, we can think about big events that pile up debris from something rising 30 feet above flood level. That organic matter will be decomposed, eventually, and the soils mixed into that mess. It will be converted into mud, or be blown away to a new landing spot as it dries. This flow compression point, known as Wallula Gap, is where these massive flood events went from 50 miles an hour to a complete pause. Heavy boulders, trees, and icebergs paused here. Some still remain today, those sunk to the bottom. Some reside on the 11,700-year-old shores. We call these glacial erratics. Wallula Gap became the pour point of Lake Loess. Erosion resulting from Missoula floods has extensively exposed these lands, laying bare many layers of the basalt flows through the lower Palouse River, the Columbia River Gorge, and throughout the channeled scablands. Consider those soils and organic matter that were scoured and pulverized by the massive floods. They were held up at Wallula Gap to create Lake Loess. Another massive lake was formed, but this time it created a slack water pool. Sediment fell to the bottom, and the water filtered out and down the Columbia River. Lake Loess was formed by restricting water flow from the periodic and cataclysmic floods from glacial Lake Missoula, pluvial Lake Bonneville, and perhaps from subglacial outbursts backed up and through the constriction formed by the Wallula Gap. Water backed up, enlarging Lake Loess. Everything had to make it through the gap, passing inspection by the twin sisters. The water remained for indeterminate periods before the floodwaters drained through Wallula Gap, and the obstruction they carried. Lake Loess reached an elevation of about 1,200 feet, 370 meters, above sea level before subsiding. We will study weather patterns in more detail soon, but marine polar air systems blow up the Columbia River Gorge from the Pacific Ocean to all points east. This pattern today attracts the windsurfers to the Columbia River, and we know that 11,000 years ago it did as well. This system passed through the Wallula Gap, blowing dry Lake Loess debris soils, making mud into silt and delivering it downwind. The soil particles of just the certain size and weight dropped from the dust cloud and fell to the earth. A certain weight and size landed on what became known as the Palouse to make what would ultimately become the most productive wheat-growing land in the world. Those are known as Loess soils. Camas Prairie is the poor stepsister of the Palouse because their soils are a little less rich, lighter than the soils found only 50 miles to the west. Farmers who know the most about where growth comes from have told me Loess soils equal agricultural productivity. Strong winds blew across the Palouse, first passing Portland, picking up and scattering large volumes of silt, ground into fine powder by glaciers, and combined with topsoils through eastern Washington and Oregon. Most of the world's best agricultural lands have Loess soils. When this wind-blown silt settled, it formed the rolling, dune-like hills of the Palouse with their rich topsoil. These soil layers persist today. Kamiak Butte itself is an island, consisting of Precambrian quartzite projecting approximately 1,000 feet, 300 meters, above the surrounding wheat fields. The reddish rocks once formed the bed of an ancient sea, and the grains of sand embedded in them can still be seen glittering in the sun. These lands were historically covered by Loess soils, long before the silt from Lake Loess was formed. Then the Loess soil layers were added as glaciers from Montana, along with the glaciers in Utah, sending glacial flooding events through this Columbia River canal. All landscapes of this region are covered with Loess soils. Many covering the flood basalts are 40 feet thick. Sometimes less is covering, like several feet. But when precipitation falls on these soils, it percolates through until it hits a mostly impermeable basalt layer. This creates a concentration of nutrients from the soil. With resident moisture, plants can reach with roots. Little water is lost to the plants growing here. Loess soils overtopping the quartzite substrate present a different challenge. When water filters through these top layers, it reaches the very permeable composite. Water moves quickly through these materials, escaping the roots of annuals, shrubs, and trees. This is one of the reasons you will not see wheat, barley, or lentils being commercially grown on these quartzite buttes. Isostasy is basically forces to put balance at the Earth's surface into an equal standstill. Equilibrium in the Earth's crust is scaled such that forces tending to elevate land masses balance the forces tending to depress them. When the materials on the surface are extremely heavy, an offset is established. Then, if the weight is removed, an offsetting weight distribution is effected. Isostatic compensation is the process in which lateral transport at the surface of the Earth by erosion or deposition is compensated by lateral movements in a subcrustal layer, also known as isostatic adjustment or isostatic correction. We can initiate this example in terms of ice sheets and something we call post-glacial rebound. The formation of ice sheets can cause Earth's surface to sink. Conversely, isostatic post-glacial rebound is observed in areas once covered by ice sheets that have now melted, such as around the Baltic Sea, Hudson Bay, and the Olympic Peninsula. As ice retreats, the load on the lithosphere and asthenosphere is reduced, and they rebound back towards their equilibrium levels. In this way, it is possible to find former sea cliffs and associated wave-cut platforms hundreds of meters above present-day sea level. The rebound movements are so slow that the uplift caused by the ending of the last glacial period is continuing even now. In addition to the vertical movement of land and sea, isostatic adjustment of the Earth also involves horizontal movements. It can cause changes in Earth's gravitational field and rotational rate, polar wonder, and earthquakes. Since the retreat of the last glacial period on the Olympic Mountains, the region is showing response to isostatic rebound of the terrain. This started when the heavy ice sheets of the repeated glacial periods, the Pleistocene epoch, compressed the landforms, depressing the Earth's crust into the mantle below. As this happened, the absolute altitude of the landforms lowered under the weight. At the same time, sea levels dropped because water was being retained in glaciers around the world. In relative terms, the lowering of sea level was faster than the compression of the mantle in this region, and relative sea level change was witnessed as lowering sea levels and lowering land forms. The marine shorelines of the Washington coastline existed far to the west of the current location. The iso-elevation lines indicate the rate of rebound, the isostatic response the Olympic Peninsula is experiencing currently. I expressed these as millimeters per year. This has been recorded using physical samples taken since 1940 along this non-volcanic landscape. Some areas are surrounded by zero-rate changes of synclines. Expansive areas are moving at differential rates of rebound. Some of the areas still have active glaciation, like the summit of Mount Olympus. This Sitka spruce tree grows along the Pacific Ocean shorelines near Tuhola, Washington, the tribal headquarters of the Quinault Indian Nation. This tree, as of 2020, was 104 years old. The tree sprouted and grew in soils hundreds of feet inland of the shoreline. Through time, the shoreline has eroded inland about 250 feet, as the land surface has risen approximately 1.2 millimeters per year, that is 124.8 millimeters, or 4.91 inches, over the 104-year period since this tree sprouted. This tree appears to show that slow and pervasive uplift has washed soils around these tree roots away, slow enough that the tree has grown bark around the roots, as if it were bark around the tree bole. Roots at the ends of these spider leg roots are still persistent. Isostatic rebound has returned the soils here up 5 inches. However, at the same time, the Washington state coastline is being pressed by the Juan de Fuca oceanic plate against the continental plate to mold the accretionary wedge which forces new material against this shoreline. The combination is to create the uplift, which gives this unique and storytelling image of spruce tree with spider legs. The enormous weight of glacial ice caused the surface of the Earth's crust to deform and warp downward, forcing the viscoelastic mantle material to flow away from the loaded region. At the end of each glacial period, when the glaciers retreated, the removal of this weight led to slow and still ongoing uplift, or rebound, of the land and the return flow of mantle material back under the deglaciated area. Due to the extreme viscosity of the mantle, it will take many thousands of years for the land to again reach an equilibrium level. We are all in a state of change. Jumping back to this again, think about the flood basalts pouring over about 40% of Washington state and adjacent areas in Idaho and Oregon. There are lands with 2 to 3 miles of these very dense and heavy basalts. Unlike glacial ice, basalt flows do not melt. What did that do to the elevation of eastern Washington? Logically, we can conclude it compressed the lithosphere and lowered elevations. But by how much? Kamiak Butte today stands at 3,641 feet, or 1,109 meters. What would the elevation have been had the flood basalts not compressed the entire region? How about we look to the east? Blodgett Mountain Peak, in Idaho, is located 135 miles southeast of Kamiak Butte, standing at 2,635 meters, or 8,647 feet. These two summits are in different geological provinces, and were created under only juxtapositionally similar situations. However, this area of Idaho was not directly impacted by the flood basalts witnessed in eastern Washington. The forces we see here give meaning to the deep dynamic isostasy of this persistent and dense layer forced out of the lithosphere below to reside on top of it all. This is where eastern Washington, parts of northern Idaho and Oregon, could be now if these flood basalts had not been poured here. Kamiak Butte's elevation might be over twice its current elevation, like Blodgett Mountain at 8,650 feet. Some geologists have estimated Kamiak Butte might have peaked at 10,000 feet without those flood basalts pushing it down. The events we discussed today are built on the back of the tectonics of the landscape which brought the Palouse Hills to their current condition. There are more geologic events. We have scraped only the surface thus far. There are large and significant volcanic events that have happened in the Cascade Range, like Mount Mazama in Oregon, blowing its entire complex volcanic structure in an eruption 7,700 years ago, or Mount St. Helens blowing only 40 years ago. Ash from these events, and others, are scattered on the surface of this region to become part of the nutrient cycle used by plants growing here. The herbivores eat those plants and grow. This is their restrictive environment where they thrive and survive. We will keep attention on this pulse of life.